Sometimes the universe just refuses to follow our script. You spend years thinking you've got the rules down, Newton, Kepler, Einstein, all those equations lined up, and then something out in the dark flips the table. The math stops working. Predictions fall apart. Out there in the middle of the night, you sit in a control room surrounded by humming computers, staring at data that simply won't behave. Models crash, warning lights flash, and suddenly all that careful knowledge starts looking flimsy. October 30th, 2025. Yeah, that was one of those nights. A visitor from another star came swinging around our sun. Just a lonely chunk of ice and rock drifting for who knows how many millions of years, and then suddenly it did something none of us expected. We'd been tracking it for months, pinning down its position with ridiculous accuracy, kilometers over distances where Earth itself is just a speck. We mapped its orbit, ran the numbers. Everything lined up. We thought we knew exactly where it was headed, but then it didn't go there. Not quite, just a little off. Not some dramatic Hollywood swerve, no flaming engines, no wild turns, just a small nudge barely noticeable. A tick in its velocity, a slight change of course, enough to mess up the predictions, to make the calculated path drift away from reality. Suddenly, the numbers stopped adding up. The orbit shifted in ways gravity alone couldn't explain. Astronomers have a name for this: non-gravitational acceleration. Comets do it all the time, outgassing, spinning, losing a bit of mass. Usually you see the cause, it's messy, but it makes sense. This time though, it didn't look random. It looked intentional. Honestly, it felt like a course correction. When that happens, when something in space moves, not just because of gravity, but for a reason, scientists get quiet. You can feel it in the air, in the way people talk in meetings. The safe, familiar rules of celestial mechanics start to feel shaky. Nobody wants to come right out and say what they're thinking. What pushed it? Why that direction with that precision? The question lingers unspoken but everywhere. We're wired to see patterns. It's how we survive. We spot danger, connect dots, even when the connection isn't there. In science, that instinct is both our gift and our curse. It helps us find the laws of the universe, but it also tricks us into seeing purpose where maybe there's just accident. That's the problem with 3IATLAS. Did we just see a pattern in noise? Is this all coincidence and paranoia? Or is it real, and if it is, what does that mean for everything we thought we knew about what's out there? The discovery itself wasn't dramatic. It came through routine tracking, just scientists and their machines, logging positions like they do every night. Observatories all over the world, Chile, Hawaii, Arizona, the Canaries, keeping tabs as 3IATLAS whipped around the sun and started heading back out into the dark. Nothing special, just standard operating procedure for a comet. Well, except this one came from another star, and for most of us, you only get to see something like that once in a lifetime, if you're lucky. Tracking these objects is a weird mix of boredom and excitement. You spend ages glued to a screen, watching numbers stack up in spreadsheets, double-checking calibrations, trying not to miss anything as the data trickles in. You're always correcting for little things, instruments drift, the atmosphere distorts the view, all that. It's not glamorous, but buried in those columns of numbers, right ascension, declination, velocity, brightness, there's real magic. Each data point is a glimpse of something ancient and utterly strange, something from a place we'll never visit. These objects come from other star systems, places that barely show up as pinpricks in our biggest telescopes, and here they are dropping clues into our spreadsheets. Everyone expected 3IATLAS to behave itself after Perihelion. The plan was, it'd come out from behind the sun, stick to its hyperbolic path, fade as it drifted away, and vanish back into deep space. The predictions weren't guesswork. They were solid, built from hundreds of inbound observations. We ran all those numbers through orbital software that's been sharpened over decades. It considers everything: the sun's pull, all 8 planets, even the heftier asteroids that could nudge a trajectory over time. These models have to work. We use them to steer spacecraft across the solar system, threading between planets with barely any room for error. But then November hit and the new trajectory data didn't line up, not even close. It started on November 3rd when several observatories reported 3IATLAS in the wrong spot, enough of a shift that it wasn't just a measurement blip. If it had only happened once, maybe you'd blame a glitch, some bad weather, a wobbly telescope. But it wasn't just one place. Observatories all over, using different gear and different methods, kept seeing the same thing. The object wasn't where it was supposed to be. By November 5th, it was obvious. 3IATLAS had moved. Its orbital elements, those numbers that define its path like semi-major axis, eccentricity, inclination, argument of perihelion, all of them had changed. On paper, the shifts looked tiny, just fractions of a percent. In most cases, you'd ignore something that small. But in orbit calculations, tiny changes snowball. A small tweak to velocity now turns into a huge position error later. Shift the direction by a hair, and suddenly the object is hundreds of thousands of kilometers off course. And these weren't random blips. The shifts lined up, pointing to something real. Some physical process had nudged the object. The changes just didn't fit with plain old gravity. When you crunch the numbers for an orbit using gravity alone, sun, planets, the works, you get a neat, predictable path. You know where something is going to be, almost to the meter. That's how the math works, and it's been reliable for centuries. But 3IATLAS was off script. The way it deviated screamed that something extra, something not gravitational, had pushed it. By November 15th, after more observations from around the world, optical telescopes, radar, even a few radio experiments, it was clear. No doubt left. 3IATLAS had experienced a non-gravitational acceleration. This wasn't just a theory. The data nailed it. It wasn't a fluke, not a miscalculation or a bad instrument. The object's speed jumped by about 0.03 kilometers per second. Break down the direction and there's a pattern. The acceleration had both radial and tangential parts, but the main effect was tangential. It gave the object a boost along its flight path. Astronomers call that a prograde acceleration. That acceleration, just 0.03 kilometers per second, doesn't sound like much, right? It's about 100 kilometers an hour, slower than you drive on the highway. You'd barely feel a change like that in a car. A couple seconds and you're there. But we're not talking about a car. We're talking about something with a mass in the billions or even trillions of kilograms. Picture a mountain of ice and rock barreling through space. Shifting that much mass by even a tiny bit takes an unbelievable amount of force. The momentum change is off the charts. You either hit it with a massive shove for a split second or push steadily with a decent force over a longer stretch. Either way, you're burning through a huge amount of energy. Now here's the part that made everyone uneasy. The direction of the acceleration is what really stood out, what turned this from a quirky comet story into something a lot more interesting. When you break down the change in velocity, split it into the part going toward or away from the sun, radial, and the part going sideways, tangential, you can see exactly where the push happened. For 3IATLAS, the acceleration had both components, but most of it was tangential. That means it sped up along its path, a prograde acceleration. Comets do this all the time when they're venting gas, but the precise size and direction of this push, once you run it through orbital prediction software, gives you a result that's hard to shrug off as random outgassing. Suddenly, the comet's path swings much closer to Jupiter than it would have before. Jupiter's the heavyweight of the solar system, sitting out at 5 astronomical units from the sun, its gravity reaching tens of millions of kilometers in every direction. Jupiter's hill radius, the zone where it rules gravitationally, is where moons circle and where spacecraft aim when they want to catch a ride. Now, thanks to this weird little jump in velocity, 3IATLAS is heading right for that region. Tracking something through space is basically a big gravity puzzle, but it's one we know inside and out. The sun tugs hardest, keeping everything more or less in its grasp. The planets pull too, especially Jupiter, which is more than 300 times Earth's mass and can really yank on anything passing by. Even Mars and the big asteroids chip in. Nothing escapes the math. Every massive object in the solar system adds its own twist, building up this tangled web of gravitational forces that everything has to navigate. How do you figure out where an object's been and where it's headed? You track its position against the stars, measuring down to fractions of an arcsecond. Do this at different times and you can retrace its steps, then look ahead to see what's next. That's orbital determination, one of astronomy's oldest, most reliable tools. You gather as many observations as you can from as many places as possible. Each one gives you a direction in the sky, right ascension and declination. If you can measure distance, using radar, parallax, whatever, you get the full 3 dimensions. Watch it over time and you see how its position changes, and from that you get its speed. With position and velocity at one point, you can nail down the 6 orbital elements that tell you exactly how it moves. The math behind all this is beautiful and rock solid. We've tested it for centuries, honed it to ridiculous levels of accuracy. Comets, asteroids, planets, moons, spacecraft, they all follow the paths gravity draws for them. We can predict eclipses decades out. We can chart planetary positions centuries ahead with errors that barely register. We send spacecraft across billions of kilometers and they arrive within minutes of when we planned. All those successes prove it. Gravity behaves. The math holds up. The models work. Sometimes, though not often, something besides gravity starts messing with a comet. For comets, that extra push usually comes from outgassing, when the sun heats the comet up and the ice inside turns straight into gas. No liquid phase, just solid to vapor, thanks to the near-perfect vacuum out there. Water, carbon dioxide, all sorts of volatile stuff, they just pop into gas and jet away. Those escaping gases drag dust and little bits of rock with them, which is how we get those glowing comas and long, dramatic tails that make comets so eye-catching in the night sky. But there's another side to it. The gas doesn't just drift away. It actually gives the comet a little kick in the opposite direction, like a tiny rocket engine firing. These jets aren't huge, but they're real. Over time, with every orbit, that repeated outgassing nudges the comet off its pure gravitational path. It's not a big effect, but astronomers have measured it for years. They call it non-gravitational acceleration. The name sounds fancy, but the idea is simple. If you know how fast the comet spins, what it's made of, how active it is, and where the gas is coming out, you can predict how much it'll wander from its normal path. For comets we've watched over and over, short period ones that come back like clockwork, we've got this down. We know how far they drift, and we can nail down their returns with surprising accuracy, even with all the messy chaos of jets and outbursts. But then there was 3IATLAS. This comet didn't play by the usual rules. The acceleration it showed just didn't fit the standard outgassing model. It was way too strong for the amount of gas and dust astronomers actually saw. The James Webb Space Telescope and a bunch of ground telescopes picked up the usual suspects: water vapor, carbon dioxide. So yes, it was active. But nothing about the dust cloud or the brightness suggested it was letting off enough gas to justify that much of a push. The numbers just didn't add up. The comet wasn't losing mass fast enough for regular sublimation to explain what was going on. And it wasn't just the amount, it was the direction. Normally, comets are a mess. Lopsided, rough, spinning objects with jets that switch on and off as sunlight hits different spots. You get these unpredictable nudges that, over time, sort of average out into something you can calculate. But it's never neat. Not with 3IATLAS. Its acceleration wasn't smeared out or random. It was focused, clean, aimed almost perfectly in the direction needed for a very specific change. One that would nudge the comet right toward Jupiter's gravitational domain. Not sort of in the right direction. Not close enough given the usual uncertainties. Right on target within measurement error, about as exact as you could ask for. The odds of random outgassing jets lining up just so, at just the right moment, are tiny. Not zero, but small enough to make you pause and wonder if you're just seeing an absurd coincidence or if something else is going on. And the timing, that was strange too. This sharp acceleration didn't show up just anywhere. It happened right after perihelion, during the 40 to 60 hours when the comet was hidden behind the sun from Earth's view. That's the kind of detail that doesn't feel random, more like choreography than chance. Scientists aren't fond of saying something's impossible. It's not a word that shows up in published papers. Too absolute, too final. Science is all about probabilities, margins of error, and phrases like highly unlikely or inconsistent with current models. Even when the data looks like it's breaking the rules, scientists hedge. They leave the door open for being wrong, for missing something, for the universe to surprise them again. Behind closed doors, emails, conference calls, those late nights after symposiums, the word kept sneaking in. Impossible. What 3IATLAS did just shouldn't happen. Not for something that size, with the kind of mass we estimated. Not with the activity levels we saw, which, sure, were interesting, but honestly nothing wild compared to other comets. And not without reaching for explanations nobody really wants to touch. Ideas that start to tiptoe into the danger zone where scientific reputations quietly vanish. The story of 3IATLAS starts like every interstellar visitor story, routine, until suddenly it's absolutely not. July 1st, 2025. The Atlas Survey Network, robotic telescopes always on the lookout for near-Earth objects, anything that could smack into our planet, spotted a faint smudge gliding across the background stars. ATLAS stands for Asteroid Terrestrial Impact Last Alert System. It's got telescopes in Hawaii and other places, snapping pictures of huge chunks of sky several times every night. Its main job is to catch asteroids that might be heading our way, to give us a bit of warning maybe days or weeks before they show up. Over the years, it's found thousands of asteroids. Most just drift by, no harm done. Some need a closer look. At first, this one looked like just another comet, nothing special. The solar system's packed with them, icy wanderers from way out there that sometimes swing in, heat up, grow those classic tails, then fade back into the dark. We find dozens every year. Most stay faint, invisible without a telescope, interesting only to the folks who really love studying these small frozen bodies. In the images, this new object was just a fuzzy little spot, a hint of a coma, that soft glow that marks a comet and not a sharp-edged asteroid. But then, over a few days, as more telescopes joined the chase and the data piled up, something strange popped out. The orbit didn't make sense. When you plotted its path, it wasn't looping around the sun like everything else. No ellipse, none of the familiar curves that tie comets and asteroids to our star. This thing was on a hyperbolic path, an open-ended trajectory. It would swing through the solar system just once, then shoot off into space forever. The key number here, orbital eccentricity, tells you the shape of the path. 0 is a perfect circle. Numbers up to 1 mean an ellipse, but more than 1, that's escape velocity. This one clocked in at about 1.1, way too fast to ever get caught. It was just visiting, then gone. So it came from somewhere else, the open spaces between stars. It had been drifting through that emptiness for millions, maybe billions of years, crossing light years, passing through regions where even the closest stars are just pinpricks and the Milky Way is a pale streak overhead. Interstellar space isn't totally empty, but it's close. Maybe one atom in a cubic centimeter, if that. Out there, nothing slows you down. No drag, no friction, no real forces except the faint pull from distant stars. Objects just glide, keeping whatever speed they started with, the galaxy's gravity steering them along a gentle curve. This was only the third time we'd ever spotted an interstellar object. That fact alone makes 3IATLAS a big deal, no matter how the rest of the story goes. The first, 1I/Oumuamua, made headlines back in 2017. It was weird, long and thin, tumbling end over end, and speeding up in ways we couldn't quite explain with the usual physics. People threw out all sorts of ideas. Light sails, hydrogen icebergs, chunks of nitrogen ice from far-off planets, even wilder stuff. Arguments flared up and never really settled. Oumuamua was just too strange, and it zipped past so quickly we barely got a look. The second one, 2I/Borisov, showed up in 2019, and honestly it was kind of a relief. Compared to the weirdness of its predecessor, Borisov acted just like you'd expect a comet to act. It had a proper coma and tail, it gave off water vapor and carbon monoxide, and kicked up plenty of dust. Its activity matched what you'd get from an icy body getting roasted by the sun. Scientists got to breathe out. Borisov was proof that most interstellar objects are probably just that. Visitors, comets and asteroids, tossed out of their home solar systems back when planets were forming, drifting through space until they wander into the grip of another star. Nothing strange, nothing artificial, just chunks of frozen rock cruising through the dark. The panic faded, and everyone got back to business as usual. When 3IATLAS came along, at first it looked like more of the same. Another interstellar comet, no big surprises. It showed off a coma, a cloud of gas and dust boiling off as sunlight hit the ice. The spectra looked right, all the signatures you'd expect, with water vapor, carbon dioxide, carbon monoxide, and hydroxyl radicals showing up in the data. Everything about it said comet, just one that formed around a different star, in some ancient disk of dust and gas, maybe billions of years ago, back when our own solar system was still figuring itself out. This didn't go unnoticed. The scientific community snapped to attention, like they do for the kind of event you might get once in your whole career if you're lucky. Hubble swung around and stared straight at 3IATLAS, hunting for jets or structure in the coma with its sharp-eyed cameras. The James Webb Space Telescope got in on it, too, locking onto the comet with its infrared sensors, picking up heat and molecules you just can't see with plain old optical telescopes. Back on Earth, observatories across different continents coordinated their schedules, passing the baton as the planet turned to keep the comet in view as much as possible. Radio telescopes listened for any hint of electromagnetic noise, just in case something truly weird, or maybe even artificial, was going on. Even spacecraft that were never meant to study comets jumped in. Mars orbiters with their ultraviolet gear could catch emissions from hydroxyl radicals when the geometry lined up. Solar probes like Stariaway and SOHO, usually busy watching the sun, managed to grab images of the comet as it swung around the sun's corona, tracking how the solar wind battered its gas and dust. This wasn't just curiosity, though sure, everyone was curious. This was the kind of chance that might not come again in our lifetimes, or even our grandchildren. An object from another star, close enough to study in detail, using instruments that, not so long ago, would have sounded like science fiction. A shot at real data about how planets form in other solar systems, what interstellar chemistry looks like, how diverse these wandering bodies can be. Every photon from 3IATLAS, every blip in the spectra, every scrap of information, was a clue about places and stories we'll never visit in person. This comet was a messenger from far-off neighborhoods, carrying news about planet making, comet birth, and chemistry under alien skies. The timing mattered, too, mainly because of what happened near Perihelion, the point where the comet swung closest to the sun, and everything should have gone into overdrive. On October 30th, 2025, 3IATLAS hit that mark, just inside Mars's orbit, about 1.4 astronomical units from the sun. That's around 210 million kilometers. Sounds huge, but in the solar system, that's practically next door. Sunlight at that distance is still pretty strong, about half what we get on Earth, enough to really heat up a dark surface, vaporize ices, and kick off some serious outgassing. By cosmic standards, the comet came close, but not so close that anyone worried about a collision. Nobody lost sleep over it. Astronomers knew its path inside out, had run the numbers, and watched it sail through the inner solar system on a route that kept it safely away from Earth and every other planet. Still, Perihelion, when the comet made its closest approach to the sun, was a big deal for several reasons. That's when comets really come alive, venting the most gas and dust, giving scientists a prime chance to study what these things are made of, right down to their core. It's also the best moment to see how the comet reacts to the sun's heat. Does it crack? Does it spout jets? Does it lose mass? Those observations reveal its thermal quirks and what kind of volatile stuff hides inside. And one more thing. Perihelion offers a perfect moment to pin down its orbit precisely, making it easier to spot any changes in its path down the line. But for several days on either side of October 30th, the comet simply vanished from view. From Earth, it slipped into the sun's glare, lost in what astronomers call solar conjunction. That's when the sun sits smack between us and the object we want to see. It's nothing unusual. This happens all the time. Mars disappears behind the sun every couple of years, and when it does, we lose contact with the rovers and orbiters camped out there. Spacecraft heading to Mercury or Venus pass through the same blackout period. It's just how the geometry works, a predictable, unavoidable blind spot for anything moving close to the sun from our vantage point. Telescopes can't cut through the sun's blinding light. Aim too close and you risk frying the optics, or at best, you drown your target in scattered sunlight. So astronomers set an exclusion zone around the sun, a patch of sky where it's simply too risky or pointless to try observing. The size of that blind spot depends on the telescope and how bright the target is, but for most ground-based optical scopes, it's several degrees wide. For 3IATLAS, that meant nobody could track it for about 40 to 60 hours around perihelion, depending on the exact alignment in which observatory tried. Radio telescopes hit a wall too. The sun blasts out radio waves across the spectrum, so any attempt to communicate with or listen for signals from a comet near the sun gets drowned in noise. It's like trying to whisper secrets next to a jet engine. Even the fanciest, most sensitive radio dishes can't do much when the sun gets in the way. So, for those 40 to 60 crucial hours around perihelion, tracking 3IATLAS became impossible. All anyone could do was take its trajectory before conjunction, run the math, and predict where it should pop up after the sun got out of the way. The predictions were solid, but nobody could check them in real time or spot any surprises that might crop up while the comet was hidden. That gap, those hours when the comet was unobservable, would eventually spark a lot of debate in the 3IATLAS saga. When 3IATLAS finally reappeared, far enough from the sun for telescopes to catch it again, things looked a little different. Observatories around the world picked it up on November 3rd. It was a bit dimmer than before, which made sense since it was now moving away from both the sun and Earth. Its coma, the cloud of gas and dust, looked a bit more active, probably still buzzing from its close brush with solar heat. Nothing out of the ordinary, honestly. Everything matched what people expected from a comet fresh from perihelion. But those orbital elements, the exact numbers that pin down how something moves through space, had shifted in ways gravity just couldn't explain. You wouldn't catch it in one night, but string a few nights of data together and it jumps out. The semi-major axis, which tells you how much a hyperbolic orbit bends, its negative for these wild, open-ended paths, had changed. Eccentricity shifted too, still hyperbolic, but now a touch different. The velocity vector, which is just a fancy way of saying the object's speed and direction, didn't line up with what gravity alone said it should be. This wasn't noise or some tiny blip hiding inside the error bars. The changes were real, systematic, and too consistent to ignore. Multiple observatories, different telescopes, different teams, all saw the same thing. When the numbers are off by way more than your usual margin of error, when the pattern holds night after night, you have to admit something is truly going on. The data's not wrong. The calibrations aren't off. Whatever this thing was, its path through the solar system had genuinely changed. Orbital mechanics isn't some new science experiment. It goes back to Kepler and Newton, and it's been tested and polished for centuries. We send spacecraft across billions of kilometers, and they show up almost exactly when we expect. The math is just that good. So when it stops working even a little, you can't brush it off. You need an explanation. With 3IATLAS, the actual numbers weren't huge. A fraction of a kilometer per second here, a few degrees off there. But for an object that's supposed to follow a clean, gravity-only path, even a small deviation is massive. Gravity alone wasn't enough. Astronomers always start with outgassing when a comet's path goes weird. Comets are basically dirty snowballs. When they swing close to the sun, the ice heats up and turns to gas. That gas shoots out in jets, and those jets push the comet around. It's not rocket science. Well, maybe it is, but you get the idea. Usually it's a chaotic mess, but if you measure the activity, guess at how fast it's spinning, and take a stab at where the jets are, You can build a model that more or less fits the changes you see. But 3IATLAS wouldn't play along. First, the numbers just didn't add up. The shift in velocity, comparing before and after it swung closest to the sun, was bigger than any outgassing could explain. Sure, telescopes like the James Webb and some ground-based ones saw water vapor and carbon dioxide in the coma, but not nearly enough to account for the push. The coma wasn't bright or massive enough. Something was giving this object a shove that plain old ice just couldn't manage. Then there was the direction. Outgassing tends to push comets in random directions, depending on how they spin and where the jets are. The result is usually messy, a little here, a little there, and it sort of balances out over time. But with 3IATLAS, the acceleration was weirdly clean. It pointed in exactly the direction needed to nudge the trajectory toward Jupiter's gravity. Not just close, dead on. The odds that random jets would line up that perfectly, right when it mattered most. Honestly, that felt astronomical. The third problem comes down to timing. Most of the acceleration seems to have happened right when the object was in solar conjunction, those 40 to 60 hours when we couldn't track it closely. We see its path before conjunction, right up to perihelion, then we pick it up again in early November. The change between those two tracks tells us something pushed it during that hidden window. For a natural comet, this lines up. Perihelion is when the sun's heat peaks and comets get most active. But let's be honest, this also leaves us in an awkward spot. We didn't actually watch the acceleration happen. We're piecing things together from before and after. That missing chunk of direct observation. It opens the door for other explanations. Some scientists have noted that 3IATLAS stands out for its odd composition, which could mess with how it outgasses and make our usual models less reliable. James Webb's infrared data showed it has an extremely high carbon dioxide to water ratio, among the highest ever spotted in any comet. It's way outside the usual range for solar system objects. Most comets from our neighborhood are rich in water ice, making up 60 to 80% of their ices, with carbon dioxide just tagging along at 10 or 20%. 3IATLAS flips that script. Here, carbon dioxide seems to dominate, maybe making up half or more of the ice, and water is just along for the ride. This difference is a big deal for how the comet behaves. Carbon dioxide turns from solid to gas at much colder temperatures than water does, so it can drive activity farther from the sun, even where water-rich comets would stay mostly quiet. Water needs temperatures above about 190 Kelvin to really get moving, usually inside 3 to 5 astronomical units from the sun, depending on how dark or bright the surface is. Carbon dioxide, on the other hand, starts sublimating around 150 Kelvin. With the right conditions, it stays active out to 10 or even 15 astronomical units. So maybe that weird composition led to stronger outgassing than we expected during perihelion. Maybe there are pockets or layers of carbon dioxide just under the surface that suddenly vented when the sun's heat reached deep enough, giving a quick, powerful shove that changed the trajectory. We know carbon dioxide can get trapped inside water, ice, or other materials, stable until things warm up enough for the structure to crack. Then, the gas escapes fast, causing what's called an outburst. Astronomers have seen these in solar system comets, those sudden brightenings when buried volatiles break free. It's also possible the inside of 3IATLAS is built differently than comets we're used to. Maybe it's layered in a way that concentrates volatiles in certain spots, so when those areas face the sun, you get a burst of activity. Comets probably form as ice and dust clump together gently out in the cold parts of young solar systems, building up layer after layer over eons. If the environment changed while that was happening, temperature shifts or different stuff floating around, you could end up with a nucleus where each layer has a different mix of ices. When one of these layered comets gets close to the sun, the different layers react in their own ways, creating patterns of outgassing that don't look like the simple models we use for more uniform comets. All of these are solid, realistic ideas. They don't need any wild speculation, just the regular physics of ice sublimation and heat. We've seen similar things in other comets, or at least they fit with what we know about how these materials behave. But let's not kid ourselves. It takes a lot of things lining up just right. The comet needs exactly the right mix of ices, arranged in just the right way. The venting has to kick in at the perfect moment, right at perihelion, and conveniently, right when we weren't watching. The thrust needs to point in precisely the right direction to match what we saw in its path. That's a lot of just right for one explanation. Each assumption on its own makes sense. It's not wild and you can defend it. But once you start stacking them up, something feels off. It starts to look like you're twisting the model to fit the data, not the other way around. That's the line between predicting what's going to happen and explaining what already happened. A solid scientific model gets it right ahead of time. If you keep patching it after you see the results, adding new rules, inventing exceptions, you're standing on shakier ground. Sure, maybe your explanation still works. Maybe you're right. But you lose that gut-level confidence you get from nailing a prediction. That's when scientists start to squirm. Not because they're thinking aliens or technology. Most won't even go there. But because science is supposed to be about precision. The math is supposed to match reality. When it doesn't, and you find yourself piling on epicycles and special cases just to make things add up, you can't help but wonder if you're missing something big. Maybe there's a process we haven't figured out yet, something in comet physics that just isn't in the textbooks. Maybe interstellar comets don't act like the ones we know from our own backyard. Could be that millions of years drifting through interstellar space, soaking up cosmic radiation, actually changes their makeup or how they behave when they start to sublimate. Or maybe, here's the thought no one really says out loud, but everyone's thinking, it's not just about outgassing. Maybe that's not the whole story. Maybe there's something else at play, some other force or mechanism nudging the object along. What that could be, whether it's some weird natural phenomenon or something even stranger, is a question most scientists would rather leave alone. There's another weird angle here, and you almost never hear about it in official statements or press releases. But if you hang out in astronomy circles or poke around on the right forums, it comes up. The trajectory change wasn't random. It didn't just send the comet off on some odd detour. It actually tweaked the path, fine-tuned it. So 3IATLAS is heading straight for Jupiter's Hill radius, the region where Jupiter's gravity takes over from the Sun and locks things into its own little world. After the trajectory shifted, confirmed by several independent teams running the numbers in late November and early December, they found that 3IATLAS is now aimed almost perfectly at Jupiter's Hill radius. This isn't about the comet crashing into Jupiter or skimming its cloud tops. Jupiter's 5 times farther from the Sun than Earth, and this comet's closest approach will still be measured in astronomical units. It's not even going anywhere near the planet itself. No risk of impact, no dramatic flyby, no wild gravitational slingshot sending it careening off into deep space. But the Hill radius isn't just a line on a chart. It's this vast bubble, about 53 million kilometers across, where Jupiter's gravity rules. Inside that bubble, Jupiter calls the shots. Outside, the Sun is in charge. The line between the two, the Hill radius, is where their gravitational muscle matches up. This isn't just abstract theory. The Hill radius actually shapes how things move out there. Moons circle inside it because that's where the planet can hold on to them. When we send spacecraft to a planet, we target the Hill radius for a shot at getting captured. That's where gravity makes the math work in your favor. What really stands out here isn't just the closeness of the predicted and actual paths. It's how razor-thin that margin actually is, especially after you factor in all the weird little nudges from non-gravitational forces. The intercept point for 3IATLAS, worked out from its path after swinging past the Sun and run through orbital software, lands smack in the middle of Jupiter's Hill radius, accurate to within a few thousand kilometers. That figure sounds big, sure, until you remember we're talking about a journey that covers hundreds of millions of kilometers at speeds that leave most things in the dust. Tiny course changes, sometimes just the faintest push over months, can make a world of difference. The fact that this trajectory threads right through Jupiter's gravitational sphere, instead of missing by tens of millions of kilometers, is just wild. Getting that kind of accuracy, thousands of kilometers off on a solar system scale, is basically like hitting a coin from across town. It's doable. We've done it with spacecraft, plotting out courses years ahead, correcting as we go, and still managing to arrive within a hair's breadth of the target. But here's the thing. We do it with active steering, plan corrections, constant tracking. For a natural comet, supposedly just drifting and getting knocked around by random outgassing, to hit that mark by accident, honestly, it stretches belief. Not so much that it's impossible. Nature can pull off some jaw-dropping coincidences, but enough that you start to wonder if coincidence really covers it. And that's the uncomfortable question. Most professional astronomers won't say it out loud, but it lingers in the background every time 3IATLAS comes up. Is this just a freak accident, or did something actually aim it? Think about it. A rock from interstellar space, zipping past the sun, gets shoved by outgassing in exactly the right way, by exactly the right amount, and suddenly it's threading the needle through Jupiter's Hill radius with near-perfect aim. It isn't just winning the cosmic lottery. It's winning it 5 times in a row. Sure, it happens on paper, but when it does, you can't help but wonder if someone's pulling strings behind the curtain. If this wasn't just chance, if something tweaked that comet's path on purpose, then what did it? That's where things get weird. Maybe it's just outgassing jets, firing off at just the right moments thanks to some fluke of chemistry and geometry. That's the easy answer, the one that lets everyone sleep at night. But there's always that other nagging possibility. Maybe there's a mechanism we haven't figured out yet, or maybe something happened during that gap in our observations, something that nudged 3IATLAS onto a new course for reasons we can only guess at. Jupiter's Hill radius is huge, stretching out some 53 million kilometers from the planet's center. It's a massive zone where Jupiter's gravity wins out over the sun's, a sort of cosmic harbor that keeps moons and spacecraft in line. It's where we send our probes when we want them to stick around without burning extra fuel. And 3IATLAS, its calculated intercept based on all the data we have, lands squarely in that zone with accuracy that's almost hard to believe. So we're back to the uneasy question. Is this level of precision just another fluke, or is there more to the story? For something to wander in from another star, swing past the sun, and then, thanks to some perfectly timed nudge, end up right where it needs to be, that's a lot to swallow. Not impossible, just suspicious. And if it isn't a coincidence, if something really did steer 3IATLAS just so, then what was it? Outgassing, luck, something else entirely? That's the mystery that keeps people up at night. Orbital mechanics leave no room for wishful thinking. You can't just shrug and say a comet somehow sped up at the exact right moment. The math is brutal. The physics rock solid. Plug in the real positions and speeds, do the work, and the trajectory falls out clear as day. For 3IATLAS, the numbers don't just show a random path. They show a course that got nudged, adjusted, tuned for a reason. The speed change needed to shift it toward Jupiter's Hill radius. It matches almost exactly what you'd expect from the weird acceleration seen in the data. It's hard not to feel like someone, or something, ran the numbers, made the tweak while the comet disappeared behind the sun and nailed the target. Scientists hate this kind of talk. It sounds too much like saying the comet had a plan, like something acted with intent instead of just drifting along with physics. But there's no getting around it. The data's weird. The path changed in a way that standard outgassing can barely explain, and now this thing is heading with uncanny precision for one of the most stable and useful spots in the solar system. Maybe that's just luck. Maybe you can stretch the models for carbon dioxide venting until they almost fit. Or maybe you just have to admit there's a piece missing. Something happened out there and we don't get it yet. What's really striking is how quiet the big agencies have been. NASA's official line. 3IATLAS is an interstellar comet, behaving like comets do, volatile material, outgassing, nothing to see here. Not wrong, but not the full story. The European Space Agency highlights the comet's odd makeup and the cool chemistry lessons they're getting. Again, true, but not the whole picture. Neither one has said a word publicly about the trajectory anomaly, even though researchers are passing around internal memos that flag the odd acceleration and call for more study. This isn't some big cover-up, it's just caution. Agencies don't like making claims they can't prove, but silence leaves a gap, and gaps attract wild theories. What makes this whole thing so gripping, and honestly kind of maddening, is that it's not over. 3IATLAS is still up there, still moving, still in our sights. Every night, telescopes around the globe are watching, collecting fresh data. The comet's fading as it moves away from the sun, but big observatories can still track it. We're measuring its speed, watching the coma, scanning for more weird shifts in its path. Each new reading either backs up or pokes holes in what we think happened. So far, the anomaly's holding up. The path really did change. The strange acceleration really happened. The mystery isn't fading. Science has this rule: parsimony. Go with the simplest answer that fits all the facts. For 3IATLAS, that means weird comet, weird chemistry, stronger than normal outgassing near the sun, trajectory shift that just happens to steer it toward Jupiter's Hill radius. No new physics, no sci-fi tech, nothing spooky. It's clean, it fits, it feels safe. But to buy that, you have to ignore just how unlikely this string of coincidences is. The timing, the precision, the fact it all happened while no one was watching. Each bit is possible, but stack them up and it starts to feel like you're pushing your luck. The other theories, they're even harder to swallow. If natural outgassing didn't cause the acceleration, then what did? Some hidden heat source, radioactive decay, a chemical process nobody's seen before. Those are wild, but at least they stay in the realm of nature. But there's another thought, a whisper in the halls, never out loud at conferences, but it's there. What if 3IATLAS isn't all natural? What if someone or something modified it, built in a way to steer, to thrust, to move with purpose? What if this comet was made to look like a comet, but it's really not? This is where things get tricky. The moment you suggest that some weird object out there might actually be a probe or a spacecraft from another civilization, you're basically stepping onto a professional landmine. People have wrecked their careers for a lot less. Astronomy is full of false alarms, natural stuff that looked artificial at first, patterns that turned out to be just our brains seeing things that aren't there. Scientists are trained to be skeptical, especially when someone makes a wild claim. And honestly, saying that something flying in from another star is a piece of technology instead of a weird rock, that's about as wild as it gets. You need more than just good evidence. You need proof so solid that even the biggest skeptic in the room can't ignore it. You need signals there's just no other way to explain. You need something that basically jumps up and down and yells, "I'm artificial," in a way nobody can talk around. 3IATLAS doesn't give us that. Not now, maybe not ever. What we've got is ambiguity, a bunch of data points that don't fit neatly into the usual natural explanations, but don't blow them up either. The non-gravitational acceleration, that's real. We measured it. The close pass by Jupiter, also real, and the math checks out. The timing, how it disappeared behind the sun for a bit, that's a fact too, and it left us with a window where we just couldn't see what was happening. These things are solid. But when you start trying to decide what they mean, that's where things start to slip. And let's be honest, when the facts don't pin things down, people start speculating. It's human nature. So let's stick to what we actually know. 3IATLAS was spotted in early July 2025, and pretty quickly, people realized it was on a hyperbolic path, classic sign it came from outside the solar system. Over the next few months, telescopes all over the world watched it swing in toward the sun, collecting everything from spectra to brightness measurements to images of the coma and tail. The composition caught people's attention right away. James Webb's infrared data from August and September showed this thing had loads of carbon dioxide, more than you see in most comets around here, with water showing up but not as much as usual. There was carbon monoxide too, plus traces of other gases. That mix hints it formed somewhere cold, maybe way out in another solar system, where carbon dioxide ice could actually stick around. The size of the solid core, the nucleus, is still kind of a mystery. That's pretty normal for comets, since the core's buried inside all that gas and dust. Based on how bright the thing looked, and some educated guesses about how reflective the surface might be, the nucleus could be anywhere from 400 meters to 5.5 kilometers across. That's a huge gap, the difference between a skyscraper and a mountain. Why can't we pin it down? Because we don't know how shiny the surface is, and we don't know how much of the brightness comes from the nucleus versus the surrounding cloud. If it's dark and dull, the nucleus has to be bigger. If it's bright and icy, it could be smaller. Without clear images of the core, we're left with models and a lot of guesswork. As 3IATLAS got closer to the Sun, its activity picked up, pretty much what you'd expect. Observers saw a tail start to form, first faint, then more obvious through October. The comet grew, turning from a tight little cloud in July to a sprawling structure thousands of kilometers wide by late October. Spectra showed more water vapor as it neared the Sun, but carbon dioxide kept dominating, which is kind of weird but not totally unheard of. There are a few comets in our solar system that act like this, but they're rare. The closest approach to the Sun, Perihelion, hit on October 30th at about 1.4 astronomical units. For maybe 2 days, depending on where you were and how the geometry lined up, the object was too close to the Sun in the sky to track properly with regular telescopes. Radio telescopes tried to bounce signals off the coma and nucleus, but the Sun's interference made the data messy and hard to read. By November 3rd, though, 3IATLAS had moved far enough away from the Sun's glare that optical tracking could pick up again, and the observations got back on track. The first orbital calculations after perihelion, using data from November 3rd to 10th, didn't line up with earlier predictions. The object's position and speed were off, just a bit, but enough to matter. This wasn't some fluke in the measurements. By November 15th, with more observations from different sites, the mismatch was clear. 3IATLAS had picked up a non-gravitational acceleration. The velocity change, about 0.03 kilometers per second. That probably sounds tiny, like a car on the highway, but when you're talking about something that weighs billions or even trillions of kilograms, it takes a staggering force to pull that off. What really got everyone talking was the direction of the push. When you break down the velocity change, you look at two pieces, one toward or away from the Sun radial, and one along the object's path tangential. With 3IATLAS, both were there, but the tangential component dominated. It was a prograde kick. Basically, it sped the object up along its orbit, and when you run those new numbers through the orbital software, the trajectory shifts. Suddenly, instead of skirting by, 3IATLAS is headed much closer to Jupiter than anyone expected. Now, Jupiter's spot in its orbit during this whole episode sets up a weirdly convenient situation. Originally, 3IATLAS would have missed any strong pull from Jupiter, just passing through a region where the planet's gravity barely reached. But with that acceleration after perihelion, the path bends inward, right toward Jupiter's turf, into its hill radius, where Jupiter's gravity takes over. And here's the thing. The shift isn't just in the general direction of Jupiter. The speed and direction of the acceleration seem almost tailor-made to bring 3IATLAS right up to the edge of Jupiter's hill sphere, as if someone figured out the math and dialed in exactly the right push. Could this happen naturally, just from outgassing? In theory, sure. If the nucleus spins at the right speed, and if certain spots on its surface vent gas in just the right directions, and if all of those vents fire exactly when the rotation lines them up, you can get thrust in roughly the right direction. But roughly isn't exactly. What we see here is precise, a very specific correction, not just a random nudge. That kind of accuracy means either we're witnessing a wild stroke of luck, or there's some process controlling both the strength and direction of the thrust. Some scientists suggest maybe the nucleus spins really slowly, like days or weeks per rotation. That would make the jets more stable and keep the thrust pointed in one direction, instead of flipping around the way you'd get with a fast spin. If 3IATLAS really does turn that slowly, and if the active vents happen to line up with the right vector, then the observed acceleration starts to make more sense. But here's the catch. We don't actually know the rotation period. Any brightness changes that might reveal a spin are faint and hard to tease out from the data. So, for now, we're left guessing at rotation speeds that make the outgassing story work, instead of measuring them straight out. Let's talk about the energy side of things. Getting something as massive as 10^9 to 10^12 kilograms to change speed by 0.03 kilometers per second takes a ton of energy. You can crunch the numbers and figure out how much mass needs to get thrown out and how fast to create that kind of push. For a typical comet, the gas escaping shoots out at about 0.5 kilometer per second, pretty fast, but nothing explosive. To match the observed thrust, the comet would have to throw off anywhere from 100 million to 10 billion kilograms of material, depending on how heavy the nucleus actually is. That's a staggering amount. It's high, but if the comet's really active near perihelion, it's not impossible. We've seen comets do more, though it's definitely on the upper end. But here, where things get tricky. When people looked at the coma, the glowing cloud around the comet, during and after perihelion, they didn't see signs of that kind of wild outgassing. Sure, the coma was active, but nothing out of the ordinary. There weren't any dramatic outbursts or sudden bright flashes that would scream tons of gas and dust just shot out. Everything looked steady, more like slow and steady sublimation than a massive, violent venting event. So we end up with this mismatch. The comet's path changes like it lost a lot of mass, but the coma doesn't really back that up. Maybe the stuff that got ejected was too faint or see-through to catch in the usual observations. Maybe it was shooting away from us out of sight. Or maybe, and this is always possible, we got the nucleus mass wrong in the first place, so our estimates are off. That's the frustrating thing about studying objects so far away. We can track their positions and speeds with ridiculous precision. Seriously, we know where 3IATLAS was to within a few kilometers, even as it crossed millions of kilometers of space. But we have no way to weigh it directly. We can't look at its surface or see inside. All we get is indirect data, and everything depends on guesses that could be wrong. If the nucleus is smaller and denser, then it doesn't need to throw off as much mass to get the observed effect. If it's bigger and fluffier, it needs to lose more. Without knowing the real mass, closing the energy budget is a guessing game. Now, about the timing of the acceleration, this is where debates heat up. Solar conjunction is just a matter of orbital geometry. It's totally expected that 3IATLAS would pass through conjunction. Any object coming from certain directions does. Plus, comets naturally get most active near perihelion when they're closest to the Sun, and that often lines up with conjunction. So the timing alone isn't suspicious. What does matter is that during conjunction, we can't watch the object closely. There's a gap in the data, and that means there's some uncertainty about exactly when and how the acceleration happened. We know where the object was before conjunction. Observations run right up to late October. After conjunction, starting November 3rd, we pick it up again. Comparing those orbits, you can see something changed. But we can't say if it happened gradually, in a big burst, or through a series of smaller events. Without eyes on it during perihelion, the details are lost. That uncertainty leaves the door open for different takes on what actually caused the acceleration. If you think it was just normal outgassing, the timing makes sense. Perihelion is when comets go wild, and we just missed the show because our view was blocked. But if you're not buying the outgassing story, the timing feels a bit too perfect, almost like something took advantage of the fact that nobody could watch. Both ideas fit the same facts. Both are logical. The real difference is in what you're willing to believe. Let's zoom out for a second. There's a reason 3IATLAS gets so much buzz and speculation. Right now, the whole idea of extraterrestrial intelligence isn't just sci-fi or late-night talk anymore. It's part of real scientific debates and even government conversations. In the last few years, US military and intelligence agencies have come out and said, yes, there are unidentified aerial phenomena out there, objects flying in ways we can't explain away with physics textbooks. That's not proof of aliens, but it does mean we've got mysteries in the sky. Suddenly, questions people used to laugh off don't sound so ridiculous. So when a weird object from outside the solar system shows up and doesn't act like a normal comet, of course people start to wonder. The thinking goes like this. If other civilizations exist in our galaxy, and if they've figured out interstellar travel or how to send signals across space, maybe they'd send probes out to scout other star systems. And if they did, it would make sense for those probes to blend in, look like rocks or comets, not shiny spaceships. That's good camouflage. It means the probe could give off gas jets or change direction, and everyone would just shrug and say, must be outgassing. It could cruise through the solar system without setting off any alarms. That's where the so-called Sentinel hypothesis comes in. Some scientists think advanced civilizations might plant autonomous monitors in stable pockets around stars, places where these devices could keep watch for ages without much upkeep. Jupiter's Hill radius is a prime spot. Stable, plenty of energy from Jupiter's magnetic field, and a great view of the inner solar system. If 3IATLAS seems to be heading there, and if its path looks a little too precise to be random, then yeah, it's tempting to imagine we're seeing some kind of probe deployment. But maybe is a tricky word in science. That's the crack where wild guesses and wishful thinking sneak through. It's the gap between what we see and what we want to believe. The Sentinel hypothesis is a fun thought experiment, and it definitely pushes us to think about how alien explorers might operate. But it's not a conclusion. It's just one idea among many, and it needs rock-solid evidence before anyone can take it seriously. Right now, we don't have that for 3IATLAS. We've got some strange data, things that don't fit neatly into our usual comet explanations, but nothing that blows those explanations out of the water. So, what would it take for 3IATLAS to actually be something other than a natural comet? First, it would need a way to move, some propulsion system that's not just ice turning to gas. Chemical rockets. We'd spot the exhaust chemicals and they'd be different from what comets spit out. Ion drive. Maybe, but that needs onboard power and we haven't picked up any weird electromagnetic signals. Solar sail. Only if the object had a big shiny surface and our telescopes don't see anything like that. No strange brightness, no odd spectra. Some technology we can't even guess at. Sure, but that's a dead end. If you explain everything with magic tech, you can't test or disprove it. Second, it would need brains and control, some way to decide when and how to fire thrusters, sensors to see what's happening, computers to steer. All of that leaves traces, heat, signals, power sources. We haven't found any of those in 3IATLAS. It looks cold like a regular comet. It reflects sunlight and glows with heat from ice and dust. No radio pings, no weird infrared, no hints of a machine hiding inside. If it is a probe, it's either powered down, using tech we can't even imagine, or maybe we're just not looking in the right way. Next, you need a reason. Why would anyone send a probe into our solar system? What's it supposed to look at or even do? Usually people say reconnaissance. Maybe it's here to study the sun, the planets, or even check out what kind of technology we've got. But if that's the idea, why skip Earth? 3IATLAS swung past Earth in mid-December 2025, and it got close enough that, if it had sensors, it could have gathered a ton of data on us. Thing is, nothing happened. No sudden shift in course, no unusual signals or bursts of activity that might hint at instruments turning on. It just cruised by, looking totally uninterested, on its way to Jupiter. That attitude doesn't really fit the idea of a probe on a reconnaissance mission. Unless, of course, Earth wasn't the target. Maybe Jupiter was, or something even farther out, and we were just a pit stop, background scenery. That circles back to the question about Jupiter's Hill radius. If you're a civilization advanced enough to want a long-term outpost in a star system, Jupiter's a smart choice. It's the biggest planet, has a magnetic field that puts ours to shame, and sits right where you can keep an eye on both the inner and outer planets. Dropping off autonomous monitors there actually makes a lot of sense. They could run for ages, powered by Jupiter's magnetic field, always watching what happens in the inner solar system, and they wouldn't need much help from home. Of course, all this is just speculation. It's fun to think about, but we don't have solid proof. What we do know, there's an interstellar comet that tweaked its trajectory after swinging by the sun, in a way that's tough to explain with the usual outgassing theories. Now it's heading out toward a region around Jupiter that matters, gravitationally speaking. That's the reality. Whether it's just a weird natural comet or something more, that depends on whether you think the oddities mean something, or if you trust that a natural explanation will eventually show up. Meanwhile, scientists are doing their job. They're collecting more data, fine-tuning their models, and testing every idea they can. Observations of 3IATLAS keep coming as the object heads away from the sun. Teams are watching for any more course changes, any new activity, anything out of the ordinary. Radio telescopes are listening for signals that could mean technology. Optical telescopes are tracking how its brightness changes, trying to figure out if it spins or what it's made of. Every new piece of data either fits the natural comet story or pushes against it. Right now, things are still murky. The facts squeeze into the natural explanation, but not comfortably. Honestly, there's a deeper question here. Human beings have stared up at the stars for centuries, always asking if we're alone. We built radio telescopes to catch signals from other civilizations. We've sent out messages, hoping for a reply. We look for exoplanets, ticking off thousands of worlds that might be habitable. All that work comes from something deep, a stubborn, almost instinctive need to know our place in the universe. Are we a fluke? Are we common? Is intelligence everywhere or rare beyond belief? Even finding simple life somewhere else would shake up biology and our sense of purpose. Finding intelligent life, that would change everything. But there's a weird catch to all this. If there are lots of smart civilizations out there and they've had millions or billions of years to spread, where is everyone? Why haven't we seen any clear signs? That's the Fermi paradox, the uneasy gap between how likely aliens seem and the total silence we've actually found. Maybe civilizations are rare or they burn out quickly. Maybe they're out there but don't want to be seen, either by choice or because their tech is so advanced we can't even recognize it. 3IATLAS really gets at the heart of this paradox. It's exactly the kind of thing that could settle it once and for all. If there are interstellar probes out there, if some advanced civilization actually sends out autonomous scouts to other star systems, sooner or later one would show up in our cosmic backyard. We'd spot it, start poking at it, and maybe, just maybe, realize we're staring at alien tech. But that's trickier than it sounds. Nature constantly surprises us. It throws out wild, bizarre phenomena that, at first glance, look crafted, like someone built them. Remember when pulsars showed up? People thought they were alien beacons because of that eerie, clockwork precision. Same thing with fast radio bursts. They looked artificial too, until we figured out natural ways they could show up. The universe loves to confuse us, and leaping to aliens did it too quickly usually leads us astray. So, where does that leave us with 3IATLAS? Honestly, we're in limbo. It's unsettling, but at least it's real. This thing has pulled moves that our models don't really account for, though nothing's completely off the rails yet. That trajectory shift, it's not speculation, it's measured and logged. The way it skimmed past Jupiter is almost too perfect. The timing, right during solar conjunction, muddies things further. Its composition is odd. The energy budget doesn't quite add up. Put it all together and you get a puzzle with pieces that just won't snap together. Sure, you can force them, pile on assumptions, special circumstances, a few lucky coincidences. Or you can admit you don't know and just sit with the weirdness for a while. Now, the next few months matter a lot. 3IATLAS is still out there, still trackable. If it starts pulling more non-gravitational moves, or if its path keeps zeroing in on certain targets, that points to something out of the ordinary. If it quiets down and the orbit settles into a plain old gravitational track, then maybe it's just a weird comet after all. If, on the other hand, we pick up any strange emissions, radio, thermal, anything that shouldn't be there, that changes everything. Every new observation chips away at the unknown, pushing us a little closer to the truth. What's wild is that this is all unfolding right now. We're not looking back at old records or ancient legends. It's happening live, with telescopes all over the world pointed at the same spot in the sky. The data's coming in. People are arguing, analyzing, writing papers, tweaking models. Somewhere in that mess, we'll either land on a natural explanation that ties up all these loose ends, or we'll have to stretch our idea of what's possible. And yeah, there's always this urge, especially when people talk about it in public, to either hype it up, aliens are here, or brush it off, nothing to see, folks. Both are lazy. The truth is messier. You have to hold on to the weirdness without ditching your standards for evidence. 3IATLAS is strange. That's just what the data says. Whether we chalk it up to some natural process we haven't figured out yet or something much stranger, that's still up in the air. The math is solid. The orbit, the trajectory, all of that checks out. The numbers tell the story. 3IATLAS shifted course after perihelion. The size and direction of that shift don't fit simple gravity. Something gave it a push. Maybe it was outgassing, sure, that's possible, but it means stacking up a bunch of lucky assumptions. The right mix of ice and dust, the perfect spin, the timing just so. Not impossible, just unlikely. And when something unlikely happens, especially when it almost looks intentional, it's worth asking what's really going on. The biggest lesson from 3IATLAS is pretty simple. We're not as smart about comets as we thought. For ages, we figured we had them down. We've watched them through telescopes, sent missions to fly by, orbit, even land on them. Our models for their formation and behavior around the sun are detailed, maybe even a little smug. But here's the catch. All those models come from looking at comets in our own backyard, made from the same stuff in the same solar system, under the same conditions. 3IATLAS is a whole other story. It was born somewhere else, shaped by a different environment, and spent ages drifting through interstellar space before showing up here. So, it's not really shocking that it doesn't play by our rules. Maybe what's truly odd is that we expected it to. Interstellar objects are still a new thing for astronomers. Not long ago, they were just a cool theory, something the math said should exist. Billions of wayward objects kicked out of young planetary systems, lost between the stars. The models hinted we spot them if we looked hard enough, but that was just theory. Then in 2017, Oumuamua showed up, and suddenly the hunt got real. Now, with 3 confirmed interstellar visitors in less than 10 years, these aren't just rare cosmic flukes. They're starting to look like a regular part of the universe's story. Each one has surprised us in its own way. Oumuamua was a curveball. Nothing in our solar system looked or acted like it. Its weird shape, the way it tumbled, its strange acceleration, none of it fit our playbook. It forced us to rethink what's possible out there. Then Borisov came along, and it looked almost boring by comparison. Just another comet, except it was on a one-way trip through our solar system. It proved that some interstellar visitors might be totally normal, at least on the surface. Now 3IATLAS is blurring the lines. It seems ordinary at first glance, but dig deeper, and things don't quite add up. It doesn't fit neatly into weird or normal. It's somewhere in between, pushing at the edges of our models. The bigger picture. We're on the verge of seeing interstellar objects all the time, thanks to better telescopes and sky surveys. If that's true, we need new ways to think about them. We can't just treat each one as a one-off oddity. We need to figure out how different stars and planetary systems make different kinds of comets. How does their chemistry change with the star's makeup? What happens to them after drifting for millions of years in deep space, bombarded by radiation? Instead of isolated mysteries, these objects could be tiny clues about how planets form and evolve across the whole galaxy. And let's be honest, there's always this nagging question in the background. What if one of these things isn't natural? What if it's actually a probe or a piece of tech from some other civilization? Most scientists get uneasy about that idea, and for good reason. History is full of things we thought were artificial, like pulsars or fast radio bursts, until physics gave us a natural explanation. If you want to claim something is alien tech, you need rock-solid proof. Not just weird behavior, but evidence that can't be explained any other way. 3IATLAS doesn't give us that. What it gives us is a mystery, a few odd details that strain our current understanding, but don't smash it to bits. Its path changed in a way we can measure. Its close pass by Jupiter is weirdly precise. The timing of its appearance makes you wonder if there's a pattern, but none of that is proof. It's just a comet that doesn't quite behave like the ones we know. And until we get evidence that's impossible to ignore, it's just an intriguing puzzle, not a sign of aliens. Extraordinary claims need extraordinary evidence, and we're not there yet. Right now, all we have are questions that don't fit together neatly, just enough to keep us looking up. The fact that we're even talking about these questions, about whether some interstellar object could be artificial, about the possibility of finding technology from other civilizations, shows how much things have changed. Not long ago, just suggesting a comet might be built instead of born could have ended your career. People would have laughed you out of the room, said you couldn't tell science from science fiction. Now, sure, there's still plenty of healthy skepticism, but at least the conversation is happening. We have government agencies actually investigating unidentified aerial phenomena. You've got respected scientists like Avi Loeb at Harvard laying out ways to look for technosignatures, signs of alien tech in astronomical data. There's even a new field, astroarchaeology, hunting for traces of technological civilizations by studying the marks they'd leave on their environments. Of course, not every strange blip in the data means aliens. Most of the time, it's nature being weird, or us not quite understanding what we're seeing yet. But the difference now is that we're building the tools, mental, scientific, even bureaucratic, to really dig into the question when something truly strange pops up. 3IATLAS could end up as the classic test case, the thing that makes us spell out exactly how we tell the difference between natural and artificial, what counts as real evidence and what doesn't, even if it turns out to be just a peculiar comet. The process of analyzing it this closely sharpens our methods for the next mystery, and there will be more mysteries. Interstellar objects aren't rare anymore. Our telescopes keep getting better, scanning more sky more often. The Vera C. Rubin Observatory, once it's up and running, will catch these visitors sooner, giving us a better shot at studying them before they race away. We're looking at finding dozens, maybe hundreds of these things in the coming decades. Everyone is a chance to test our theories, to see what kinds of planets and systems are out there, and to spot the oddballs that don't fit any natural mold. Who knows, maybe one day we'll stumble across something that's not ambiguous at all. An object that changes course in a way rocks just can't. Something sending out signals we've never seen from any natural source. Or maybe the composition is so strange, it screams technology. If that happens, if we get proof, it'll be a turning point for humanity. The day we find out we're not alone, that there's intelligence out there, other beings sending probes across the stars. That would split history in two, before and after. Everything would change in how we see ourselves and the universe. Is 3IATLAS that object? Almost certainly not. The evidence points to a weird but natural explanation, something cometary physics can handle, even if it stretches the rules. But the fact that we can't say so for sure, that there's still some doubt, matters. It means we're bumping up against the limits of what we know, and that's a good thing. It pushes us to look harder, think deeper, question what we thought was settled. This question, whether we're alone, whether anyone's out there watching us as we watch the sky, is one of the biggest questions we can ask. 3IATLAS doesn't answer it, but it reminds us we don't know everything. The universe can still surprise us, and honestly, that's comforting. We haven't run out of things to discover. There are still puzzles out there, still mysteries slipping through the dark, still reasons to question what we think we know. The math says what happened shouldn't be possible, yet it happened. The object's path shifted in ways gravity alone can't explain, in directions that almost seem intentional, though we can't prove it. And it all went down when our instruments weren't watching closely enough to catch every detail. Now it's on its way to Jupiter, following a path that feels precise, almost deliberate, though science can't call it that. So we're left with a decision. How do we make sense of an anomaly that doesn't fit the boxes we've built? What rules do we use when the universe refuses to play by ours? We can shrug it off, that's the classic scientific move. You just bend the oddity until it fits the mold, pile on enough assumptions about weird chemistry or strange geometry to explain it away. You make the model work even if you have to stack the deck. Safe, right? No big shakeups, nothing that rattles our ideas about being alone in the universe. The comet acts strange, sure. It didn't do what we expected, but hey, at the end of the day, it's still a comet. With better numbers and tighter models, we'll figure it out. This approach is bulletproof in a way. You can't really prove it wrong. Just keep tweaking the parameters, invent a few more unique circumstances, and you can always make the puzzle fit. Or you can go the other way, lean into the weirdness, spin it into something extraordinary. Some folks love this. They see a change in the comet's path and immediately jump to aliens. Maybe 3IATLAS isn't just a comet at all, but a probe, a visitor, a sign that we're not alone. Look at the way it zipped by Jupiter, the perfect timing when no one could see it, the oddball chemistry. Stack up enough of these details and suddenly you've got a story. We're being watched, maybe even studied by something way beyond us. That story gets the heart racing, and honestly, it's tempting. But science doesn't work on hope. The hard evidence isn't there. No radio signals, no impossible maneuvers, nothing that screams technology. Just wanting it doesn't make it real. Then there's the third option, the trickiest one. Admit you don't know. Sit with the unanswered questions. Keep looking, keep testing, refuse to jump to easy conclusions, either the dull or the dazzling. That takes real humility. Even after centuries of staring at comets and decades of sending out space probes, there's still stuff we don't get. It's uncomfortable, but it's honest. You hold the line on evidence and stay open to surprises. That's exactly where we stand with 3IATLAS. We're in the thick of not knowing, gathering new data, arguing over what it all means. The comet's path changed. That's fact, not rumor, measured by different teams with different gear. The way it shifted lines up almost perfectly with Jupiter's hill radius. That's not a hunch, it's just the math. The weird timing, right when the comet passed behind the sun from our point of view, makes it tough to pin down what actually happened. That's not conspiracy talk, it's just the limits of where and when we could look. What's still up in the air is whether these odd facts add up to something truly new, or if we'll eventually fold them into our understanding of how comets work. Time sorts this out. More observations will show if the comet keeps acting strange or if it settles down and behaves like any other chunk of space ice. Maybe a closer look at its makeup will clear up the mystery, or maybe it will just get weirder. If future visitors from outside the solar system act the same way, maybe this is just how some comets roll, or maybe 3IATLAS will turn out to be a one-off. Right now, 3IATLAS is still out there, sailing along its calculated path, holding tight to whatever secrets it's got frozen inside. In the weeks and months ahead, as it draws closer to Jupiter and the telescopes keep watching, we'll collect more clues. Some things will start making sense, other questions will pop up. Maybe we'll stumble on the detail that ties it all together, or maybe we'll just find more mysteries that leave us scratching our heads. Either way, the chase isn't over. No matter how you look at it, this is one of the strangest things that's ever drifted through our solar system. Not because we can say for sure if it's natural or artificial, honestly, that's the whole point. It sits right in the gray area, messing with our definitions, making us rethink how we even sort out these kinds of things. Here comes this interstellar visitor, changing course in ways physics says it shouldn't, heading somewhere that could be random, or maybe not. It's packed with clues about where it came from, and we're just starting to crack the code. The numbers are solid. No one's fudging the math. The trajectory shifted, a real measured change in a specific direction with clear results. That's just data. If you handed the orbital elements to any decent analyst, they'd see the same thing before and after perihelion. The tricky part is what all those numbers actually mean. Do they show nature doing something we don't get yet, or is there more going on? That's where things get messy. Until we can explain every bit of velocity change with an actual proven mechanism, something that really works under these conditions, 3IATLAS stays an open question. It's not a tidy puzzle with a neat solution. It's not proof we're being visited by something artificial. It's a mystery. It doesn't fit our models. It came from somewhere we can't reach. It cut through our cosmic neighborhood on a path that could be pure chance or maybe something planned. Come away with more questions than answers. And honestly, sometimes the most real thing you can do is just say, we don't know yet, but we're not giving up. We're watching, measuring, thinking, and throwing every idea we have at the data. we'll figure it out. Or maybe, just maybe, what looked like a simple question about a comet's path is actually a hint of something way stranger than we ever imagined. So here we are, staring at an interstellar object that does things regular comets just don't. Watching its precision as it heads toward Jupiter's gravity, maybe it's luck, but it doesn't feel that way. There's a gap in the observations, right at the moment we needed them most, and that leaves plenty of room for different takes on what actually happened. Now we have to pick, stack up a bunch of guesses to keep the natural explanation alive, or start wondering about possibilities most scientists aren't too keen to discuss. There's just no easy answer. Every way forward means either accepting some weird coincidences or believing in mechanisms we haven't proven exist. But here's what we know for sure. 3IATLAS handed us something valuable, even if we don't totally get it yet. It's forced us to look harder at our models, to rethink comet physics, to wonder what's possible out there in a galaxy full of places we'll never see up close. It's a challenge, one that demands tough, careful science, not just guesswork or armchair theories. And honestly, it's a reminder, no matter how far we've come, no matter how sharp our telescopes or tight our calculations, the universe still has a way of surprising us, making us rethink things we thought were settled. That's important too. It keeps science honest. It keeps us asking questions, even when the answers are uncomfortable or unclear. Maybe we'll eventually explain 3IATLAS with natural processes we just haven't figured out yet. Or maybe it's the first real sign that we're not alone, that someone else is out there, watching us the way we watch the sky. We don't know, not yet, but we're paying attention. We're watching, measuring, testing, and not shying away from the hard questions. And that's what matters most right now. Maybe that's the real story here. Not that we found proof of aliens, or stumbled onto a brand new kind of space object. It's that we've finally reached a point where we can dig into these questions for real, where we've built the tools to spot interstellar visitors and the brains to wonder if any of them might be more than just weird chunks of rock. We're getting better at noticing when something doesn't fit. We're building ways to judge wild claims with the seriousness they deserve. We can tell the difference between that's odd but natural and wait, that just shouldn't happen. 3IATLAS is teaching us all this, whether it turns out to be a comet with quirks or something far stranger. It's showing us the limits of what we know, the spots where our models fall apart or get fuzzy, the questions we really need to answer. And by wrestling with it, we're getting ready for whatever comes next. Stranger objects, clearer evidence. Situations where we have to make a call, one way or the other. We're learning how to do this kind of science, how to stay skeptical but open, how to keep our standards high without shutting out possibilities we haven't even thought of yet. The story isn't finished. 3IATLAS is still out there, still under the telescope, still throwing out data that could solve the puzzle or make it even weirder. Over the next few months, we'll see if it keeps breaking our models or settles into something we can actually explain. We'll gather more spectra, more brightness readings, more precise positions. Every new number narrows things down, pushes us a little closer to the truth. It's slow, sometimes maddening, but that's how science works. You collect data, you test your ideas, you tweak your models, you admit when you're stumped, and you keep going until things finally start to make sense. Somewhere in all that, maybe we'll find the answer. Maybe we'll learn that 3IATLAS is just a weird comet, a mix of stuff that made it spit out more gas than we expected, at just the right time to nudge its path the way we saw. Or maybe we'll find something that cracks open our sense of what's possible, what's out there in the galaxy, what might actually be dropping by from another star. Either way, we learn something big. Either way, the universe gets a little less mysterious, or maybe a lot more. But until we know for sure, until the data gives us an answer we can't argue with, 3IATLAS stays what it is, a mystery. An interstellar visitor that pulled off something the math says can't happen but did. An object flying toward Jupiter, its path so precise you can't help but wonder if it's just luck or something more. It's a challenge to everything we think we know, forcing us to look closer, ask harder questions, and admit what we don't know. And maybe that's exactly what we need right now, a real mystery. Something that reminds us just how much we still have to learn, how easily the universe can surprise us, and why it matters to keep watching, keep asking, keep chasing the answers even when they're uncomfortable or don't match what we expect. The numbers are clear, the trajectory shifted, and until we figure out why, 3IATLAS is going to keep us guessing and maybe a little uneasy. It's an interstellar visitor that came out of nowhere, did something impossible, and left us wondering if we're just seeing nature being weird or something else being incredibly clever.